Okay, we are here for Lesson 4, Fundamental Theorem of Similarity. Now that we've talked about dilation, we're going to go ahead and apply that to our concept of similarity. So for this discussion, you're going to need a piece of paper, a piece of lined paper, so lined notebook paper, a centimeter ruler, a protractor, and a 4-function calculator, along with your math journal and, of course, your worksheet. So the last few days we have focused on dilation. We now want to use what we know about dilation to come to some conclusions about the concept of similarity in general. So a regular piece of notebook paper can be a great tool for discussing similarity. What do you notice about the lines on the notebook paper? Well, the lines on the notebook paper are parallel, and that is, they never intersect. Keep that information in mind as we proceed through this activity. So on the first line of your paper, you're going to mark a point which we'll call O. Go ahead and make that close to the center of your paper, in between the left and the right side. We will use this as our center. So from point O, you're going to draw a ray, probably going a little bit to the left of center, but it doesn't have to be completely all the way straight out. But draw a point, or from the point, draw a ray OP, mark the point P, a few lines down the center, and then choose another P prime farther down the ray, also on one of the lines of the notebook paper. For example, you may have placed a point P 3 lines down from the center, and a point P prime 5 lines down the center. Now, the example is going to continue to use 3 lines and 5 lines, but you can pick any lines you want. So if you want to do 2 and 4, or 4 and 6, or 1 and 5, it's completely up to you. So use a definition of dilation to describe the lengths along this ray. Well, by definition of dilation, the length of OP prime is going to be equal to the length of OP times a scale factor. So recall that we can calculate the scale factor using the following computation. The length of OP prime divided by the length of OP equals R, which is the scale factor. So in this example, the scale factor R is 5/3, or 5/3, because P prime is 5 lines from the center, and P is 3 lines down. So on the top of your paper, write down the scale factor that you used. Again, yours doesn't have to be 5/3, it could be anything else. Now draw another ray, which we're going to call OQ. And you might want to draw this a little bit to the right of O, not down the center of your paper. Use the same scale factor to mark points Q and Q prime. In the example, Q is placed 3 lines down, and Q prime is 5 lines down from the center. Again, use the same as you did for OP, just translate it now to OQ. Now connect point P to point Q and point P prime to point Q prime. What do you notice about the lines PQ and P prime Q prime? Well, if you did it right, the lines PQ and P prime Q prime fall on the notebook paper lines, which means that PQ and P prime Q prime are parallel lines. Use your protractor to measure angles OPQ and OP prime Q prime. What do you notice, and why do you think this is so? Well, both angles are equal in measure. They must be equal in measure because they are corresponding angles of parallel lines, those parallel lines being PQ and P prime Q prime, and they are cut by a transversal, which is the ray OP. Now, without using your protractor, what do you think about the angles OQP and OQ prime P prime? Well, these angles are also equal for the same reason. They are corresponding angles of parallel lines, which are PQ and P prime Q prime, and they are cut by the transversal, which is the ray OP. So use your centimeter ruler to measure the lengths of OP and OP prime. By definition of dilation, we expect the length of OP prime to be equal to the length of OP times the scale factor. That is, we expect the length of OP prime to be equal to the scale factor times the length of OP. Verify that this is true and do the same for lengths OQ and OQ prime. As you're measuring with your centimeter ruler, go ahead and round to the nearest millimeter. So if you have 3 centimeters and 5 millimeters, then you would just round that as 3.5. Alright, so here's a sample of what your paper should look like right now. You have, again, a ray starting from O, going down your paper, and again, you could have picked any lines, but for our sample, we did 3 and 5. So if you did 1 and 4, or 2 and 6 or something like that, yours will be different according to that. But the key idea is when you do OQ that you pick points on the same line so that you're getting parallel lines that correspond to your notebook paper lines. And then you're going to start measuring your lines, and again just rounding it using decimals. 3.7 is 3 millimeters, 7 centimeters, but we're going to keep it in centimeters. And as you write these down, you should compare them. If I did 6.2 divided by 3.7, I should get the same scale factor of 5 to 3. Alright, bearing in mind that we have dilated from the center points P and Q along their respective rays, do you expect the segments PQ and P prime Q prime to have the same relationship, meaning that the length of P prime Q prime is equal to PQ times the scale factor? Write in your math journal why or why not. And what we mean by that is, going back to our sample, this measurement right here, is it proportional or similar to this measurement right here? Alright, continuing on. So measure the segments P, Q, and P prime, Q prime to see if they do have the relationship of the length of P prime, Q prime is equal to the original length PQ times the scale factor. So it should be somewhat surprising that in fact the segments enjoy the same properties as the segments that we actually dilated. So now mark a point A on line PQ between points P and Q. Draw a ray from center O through point A, and then mark A prime on the line P prime Q prime. Do you think the length of P prime A prime is going to be equal to the length of PA times the scale factor? Check the segments and use your calculator to check or measure the segments, and then check them with your calculator. So you should notice that these new segments also have the same properties as the dilated segments. So now mark a point B on line PQ, but this time not on the segment PQ. That means not between the points P and Q. It's going to be to the left of OQ, your ray OQ. I'm sorry, not to the left, to the right. Again, draw the ray from the center O through point B and mark point B prime on the line P prime Q prime. Select any segment, either AB, PB, QB, and verify that it has the same properties as the others. So this is what it should look like, meaning B is to the right of OQ, so that A was in between P and Q, and B is to the right of Q. So if you need to make changes to your drawing, just go ahead and make those modifications. So now you're supposed to measure these as you continue to measure and compare, like QB and Q prime B prime, or you could do A to B and A prime B prime. You should notice, and here's the beginning of the work, that as you measure these, again another sample of a drawing, that these should all be similar, and everybody in class, no matter what their drawing looks like, this should be similar all the measurements should be similar and reflect the scale factor of whatever it is you chose. So will this always happen no matter the scale factor or placement of points P, Q, A, and B? Well, yes, we believe this is true. One main reason when you come back to class we can verify this is that everybody has probably picked different points and are sure many of us use different scales. So that's one of the things we'll be doing is comparing your drawing to the other people at your table and in the class and having that discussion to see that the scale factor is the same for each person. So describe the rule or pattern that we have discovered in your own words in your math journal. We're not going to check this quite yet, but go ahead and try to write what you see happening in your own words in your math journal. Go ahead and continue the video when you are done. Alright, continuing on. So we have just experimentally verified the properties of the Fundamental Theorem of Similarity, which we can abbreviate as FTS, in terms of dilation, namely that parallel line segments connecting dilated points are related by the same scale factor as the segments that are dilated. So the theorem should sound like this. Given a dilation with a center O and a scale factor R, then for any 2 points P and Q in the plane so that O, P, and Q are not collinear, the lines PQ and P'Q' are parallel, where P' is the dilation of P and Q' is the dilation of Q, and furthermore, the line segment P'Q' is equal to the line segment PQ times the scale factor R. So now that we are more familiar with the properties of dilations and similarity, we will begin using these properties in the next few lessons to do things like verify similarity of figures. Alright, you have exercise on your lesson worksheet. Go ahead and complete that and then continue the video to check your answers. Alright, this is what you should have after doing the exercise. Go ahead and check your answers. Again, pay attention to the symbology being used and the way that the answers are being explained. If you have any questions, write them down and be prepared to bring them to class. Alright, so let's go ahead and close this out. First of all, we know that the following is true. If a line segment, a dilated line segment, is equal to the original line segment times the scale factor, then in other words, under a dilation from a center with a scale factor R, a segment multiplied by the scale factor results in the length of the dilated segment. We also know that lines PQ and P'Q' are parallel. So even though that wasn't our original part of the drawing, the consequence is we have parallel lines and therefore those lines are also verified by the Fundamental Theorem of Similarity in terms of dilation using an experiment with notebook paper. The fact that the parallel lines PQ and P'Q' are also going to be dilations of each other. Alright, we'll see you in class.